Hey everyone, I wanted to explain how this activity is going to work regarding VSEPR and three-dimensional shapes. You're going to get this handout in Google Classroom. It's called VSEPR Shapes. And on this handout, what you're going to see are columns labeled steric number, lone pairs across the top, and down here, 2, 3, right? These refer to what's known as the steric number. I've gone ahead and done this first example for you, and I'll show you how to do another one. The steric number is the number of groups around a central atom. Now, they could be bonded electrons, as they are in this example, because you have an atom, a bond, atom, bond. What this represents is two bonded groups. Although, as we become more complex and we go to 3, 4, 5, and even 6 groups surrounding an atom, not all of them will be all bonds. Notice that 0 lone pairs means only around the central atom, and here there are no lone pairs, only bonded groups. As we become more complex, and as molecules take on 3, 4, 5 groups around a central atom, that's where we can have lone pairs. So what you're going to do is you're going to click this link and you're going to go and find this simulation. You'll see a home screen that looks like this, and you're going to click the model and enter the models first. Now, the simplest of all, right, the simplest of all models would be this linear shape. Notice that I can attach a single, double, or even triple bonds. And when I attach two single bonds, what this does is this shows me the angles. Now, as we talked about in the PowerPoint, um, when you have two bonded groups, really the maximum angle that you can get is easily seen as at 180. And it doesn't matter if those are single or double, because also, as I said in the video in the PowerPoint, double bonds are treated as single repelling units. So even though this is 4 electrons total in this shared bond, what we see here is it's still forming a 180 because these electrons are one single repelling unit because they go to and from the same two atoms. If these boxes are not checked on the bottom, I want you to go ahead and check them. And if this angles, show bond angles, isn't checked, I also want you to go ahead and check that. Notice that what this tells you is molecular geometry and electron pair geometry. And here's the difference between the two. Electron pair geometry is the total number of repelling units, bonded and non-bonded. When there are 0 non-bonded electrons around this central atom, like there are in our case right here, the molecular geometry and the electron pair geometry are the same. Notice they both say linear. The electron pair geometry is the total number of repelling units around the central atom, bonded and non-bonded, and the molecular geometry is just the bonded. When there are no lone pairs, they are the same. Notice you get a linear molecule. So I want you to make a linear molecule, just like I did, and take a look at it, see how whether you get double or triple bonds, it doesn't matter, you have a linear shape whenever there are two non-bonding groups. Obviously, it's going to get a little more complex. So what I want you to do is to do a quick rearrangement, take a screenshot, go back to your handout, and then insert a screenshot with the angle shown. Here, MG stands for molecular geometry. You'll also see it referred to as molecular shape. They are the same thing. And we found out that when they're at the two bonded pairs, you have a linear molecule. Because there are 0 lone pairs, there's no distinction here. It's also linear. EPG is the electron pair geometry. And then finally, there's something I want you to add called, it's sort of a special notation where X refers to the bonded pairs and E refers to the non-bonded or lone pairs, and I showed you there what it means. A is just means one central atom, which is all these are going to be because there's no subscripts. The subscripts in here refer to how many of them. Notice that this would be AX2 because the only two groups surrounding this central atom are bonded electron pairs because there's atoms attached to either end. There is no E. You might even see E subscript 0 when there are no electron pairs. Now I'm going to do another example with you. I'll show you how this works here, and then you're going to move forward and do all the rest. Notice I've just put X's in these boxes that there really is nothing that applies, right? If this were a lone pair, this would be linear too. It's really not something that you think about. However, with each increasing number of surrounding steric groups, you get a lot more options where one lone pair, two lone pairs, three lone pairs become a thing. So let's go back and we're going to look at 3, and let's start again. Let's start with nothing. Now, if we have 1, 2, 3, what you'll notice is you have 120 degrees. And what you'll also notice, and this is why I love this simulator, is you can see that it's flat. Don't just look at what they show you. I want you to turn it, manipulate it, and really understand the fact that this is flat. Do this for every single structure. Now, what you'll notice again is they now tell you what the new names are. And they tell you what all the angles are. So what you're going to do is you're going to take a screenshot of this. You're going to go back to the handout, and you're going to write trigonal planar and trigonal planar. Again, they are the same because there are 3 groups surrounding and they're all bonded. So the molecular geometry and the electron pair geometry are trigonal planar. So you would go back, insert your screenshot here, trigonal planar, trigonal planar. Sometimes you have to scoot down. I even showed you how this is shown as AX3, and then the EX for the examples you're going to fill in later, and I'm going to first do these. Worry about these examples later. That's where you're going to use the other tab of real molecules. Now, what if I take one of these away and I insert a lone pair? Again, make sure this box is shown so that you can see what's happening. Now, they don't show us here an angle between the non-bonded or lone pairs. Right now, I want you to just write 120. However, as I explained in this previous video, here's where this simulator is a little bit falls short. This non-bonded pair is more repulsive than the bonded pairs here. So technically, and as we'll talk about a little bit later, you really should write this down as less than 120 because this angle is going to be squished in because these repulsions are less than these repulsions here. So really, go ahead and if you can, really try and identify these by putting in less than 120, noting that this is going to be more repulsive. Now you're going to go back, and where are you going to put this? You're going to put this picture here, because what this represents is one lone pair, but you still have 3 steric groups. You have bonded, bonded, and lone pair. So there's still 3 steric groups. Notice here, though, they're no longer the same name when we're talking about the molecular geometry because these are both trigonal planar, okay? Because we're still talking about 3 electron pairs total. EPG, the electron pairs, is everything added up. Molecular shape is just the bonded. So when we go back, I want you to write down the name of this shape, and it's called V-shaped or bent. I think you understand where this is going now, right? I want you to go through, and then you're going to add, let's take away our lone pair. And now that we've gone across, right? Now that we've gone across, we're not going to have two lone pairs because again, if you really envision it, right, you can even make it yourself. That would just give you back a linear molecule. So now then I want you to move on to 4 and then 5, and then notice that each time you're increasing the number of lone pairs. Lastly, let's revisit this because the X3 here is referring to the fact that they're all bonded. X, as we go back up, means there are 3 bonded groups alone. E is when you have lone pairs. That's why this one is now AX2E, because when you look back at this, right, A, X, X, E. The X's are the bonded pairs. So now you're going to go through taking screenshots and inserting, and you're going to use this as a reference later to study from. The last part of this activity is I want you to see here and go through what all of these examples are. When you click water and you say show bond angles and then you say show electron geometry, what we're going to see is, because water has 4 repelling units, 2 of which are lone pairs, 2 of which are bonded pairs. And the electron pair geometry of 4 is a tetrahedral shape. However, the molecular geometry made only of the bonded pairs is what's called bent or V-shaped. And again, instead of writing 109.5, I hope you realize here that this is a non-ideal geometry of less than 109.5. And technically, because there's 2 non-bonded lone pairs here, this is extra repulsive. And what's going to happen is these 2 are going to get squished even closer. So you might even write less than, double less than 109.5. So then just go through all of these, look at the different examples, and then assign them here by writing H2O down here in this spot with 2 lone pairs and 2 bonded pairs. Your example here would be H2O. And if you run out of examples, see if you can Google any specific examples if all of these are you're exhausted and you still have spaces left in the handout. I hope this all makes sense. I want to give you a chance to see these in 3D, and don't forget, really flip these around, because in lieu of molecular models you can play with, and in lieu of our VR sets, which are at school, sad, this is what we've got. So hope you have fun with this. Really take a look at the angles, and I hope you enjoy it.